Okay, so I hope that you continue playing with MATLAB. If you are new, I hope that you have started working on the homework, especially if it's new for you, MATLAB. But if you have any questions, etc., you should let me know, because we kind of now move from the signal processing to start to talk about mechanics, going towards wave propagation. I call the topic of today and probably on Tuesday, hopefully we'll finish it up in 2 classes, vibration of elementary systems. Now, I ask you to read a paper just for 2 reasons. One, to get a sense of why we are studying vibration, why does it matter, and also kind of to start getting familiar with this kind of literature in testing. So let's talk about this a little bit. I hope that everyone read this paper. Let's talk about first the author a little bit. So he was a professor at Penn State. He's now retired. He doesn't look like it. So the last time I saw him was in a running competition in Tossie Mountain. So he was in a running group. He's, I think, 76 or something, but in a very good shape. So that's Jay Maynard. I worked with him also, so he's certainly someone who has contributed to this field a lot. So let's talk about his work a little bit. I asked for volunteers. If there is no volunteer, then I know all of your names. So that's so kind of I put some points here, but we can talk freely about this. So let's just start with what did you understand from reading this? To some of you, this may have been completely foreign language. To some of you may have been more familiar. What did you learn? So this is resonant ultrasound spectroscopy. We call it ROS, the short term. So one point that I put here, so what is being measured? What did you learn? How does this method work?
Elastic constants are measured with this.
Mm-hmm. So the output at the end is elastic constant, but how do we get there?
They use something called
just very conceptually, how do we measure elastic constants? Because the way to measure elastic constants, maybe the one that you all know, is that you have a sample and then you start stretching it, you measure a stress, a strain, and you get Young's modulus. This is probably something all of you know. That's how you measure elastic constants. So this method also gives you elastic constant, but how?
Natural frequencies.
Yes. So you measure natural frequencies, but how do we go from these natural frequencies that we are going to talk a lot about to elastic constants? It's very useful to think about this problem as kind of what are the inputs? Let's say you go and you want to do a ROS measurement based on what you read. What are the inputs to this measurement? Yes, Ryan?
You need to know the geometry of the sample.
Excellent. You need to know the geometry. Do you remember some things you read in this paper about some simple geometries, or the first ones? He also gives a nice historical account of what's going on. So let's make this bigger. Do you remember something about that?
I think it said like spheres or just cubes.
Exactly. From in the beginning, they used, because they didn't have computers, they had to calculate everything by hand. They started from very simple measurements. Spheres or cubes, exactly. So what else? Just geometry?
Boundary conditions, like it should be having a free boundary condition.
Yeah, so did everyone see that in the paper, that having free boundary condition is kind of for the classic ROS. You actually can get around it. You can do measurements where you don't have free boundary condition, but if we have, it's good. So boundary condition, I put in parentheses free. What else? Yes?
Normal modes of the sample?
Well, this is what we are going to measure. But what is the input? When you go, let's say you come with a sample, I think, Peter, at some point, we were considering doing ROS on one of your samples, what I remember. That if you bring a sample to me, what information do you think, what else did we need?
The range of frequencies that you're going to...
That's measurement. I know, you're right. You're going ahead a little bit. I know what you're talking about.
It's prosody
Song?
from the mechanical property. You already know, like, properties or XRD without like minerals.
No, you don't need to know that, fortunately.
The speed of sound.
No. Well, now we get there, he makes a lot of arguments against velocity measurement that I want to talk to you about. That's when people doing different measurements they show rivalry. So there is some discussion about that, no?
Yeah.
Clay, did you see something else as input? Let me help you. If you think if something is just, we know that it is cubic and we know the boundary condition, would have the same natural frequencies if it has different materials?
I guess you need to know the density.
Exactly, excellent. So you need to know also the mass or density. You can know the mass from the geometry, you know the density, but what you actually need is density. Excellent. That's exactly where I wanted to go to. So you have these, and also something that I think Song mentioned, something which comes with it, but it's not the input, it's the material, right? It's the material itself. So inside, hidden here as the input, is actually the elastic tensor. It's your material, which is your testing, right? You can think about it as a hidden, what you are giving in, which is at the end the output. Now I'll show you how I want to get there. Now then, all of you told me that somewhat you need to measure modes. But before that, you actually need to have this information. You assume a certain elastic tensor. You have the geometry, mass, etc. That's the easy thing. You have to have some forward model. So in the old times, people were calculating that. And now you use console, for example. You just give in, and for whatever geometry you have, whatever boundary condition, so it becomes much more versatile. You get, you do what I call the forward modeling, and you get the mode shapes. So now you are experts. Basically, what we look at actually is both amplitude, typically, and phase spectra. I think he quickly mentions that the phase is also very helpful, and that's what in practice we use it actually. It is very helpful. So now you all know what that means when I say amplitude and phase spectra. And now, once we have all of that, then you actually do measurements. So you perform ROS, and I think all of you told me that what you measure are the natural frequencies, and you get the natural modes. So I just call them ROS measurements, whatever. And once you do this, then you need to get to the elastic tensor, you need to do inverse. You have to solve an inverse problem. And then you get some approximation of the elastic tensor. This is pretty much how it works. Now, he says something about the number of measurements versus the number of elastic constants. Anyone remembers which one is typically larger? Do we measure more modes? Do we measure one mode? No. We measure a large number of modes. How do you think that relates to the last number of elastic constants we need to find? What would be your guess? Let me make it a little bit simpler. If you have a linear elastic material, do you think you need more measurements than when you have a totally anisotropic material? No. So the more anisotropy we have, we need to take more measurements. But something else is that typically you have much more measurements, you have much more modes typically. You have redundant measurements, much more modes than elastic constants. So it becomes an optimization problem pretty much. You basically reduce the distance between your forward modeling results and the measurements. And then you get an estimation of the elastic constants. Okay. So resonance seems to be very important for this measurement. What else does he talk about? We talked about boundary conditions. Oh, he talks about different sizes. So what does he say? Let someone on this other side answers. What does he say? Does he say that your sample has to be of certain size? Tim?
No, he uses the example of a bridge over the Rio Grande that was
The large.
this method.
He even talks about the moon a little bit.
Yeah, and if it's like cheese or not.
Right, that's that was interesting. Yeah, exactly. The last part when he talks about the cheese is even more interesting about the aging. I thought that's hilarious. So I read this again and it was fun to read it again. So the answer is it's very interesting, this method, because you can test very, very tiny crystals, but you can also test really large samples and even go and test the moon. So it's very, that's a big advantage. And then something that you may have seen is he makes some comparisons between, he argues that resonance measurements are better than velocity measurements for this particular application. Do you remember how he argues that, or at least where it is in the paper? So here is the paper. Looks nicer in a... Yeah, I should have actually shown you. So here, if you see on this page, which is, I don't know, page 29, he's talking about the advantage. I think it's here. Yeah. He's comparing somewhat the Ross and velocity measurements. What does he say? How does he say that these resonance measurements are better? Of course, if you never did any velocity measurements, this would be a little bit hard for you to imagine. But he's comparing this measurement to a situation where you have a transmitter and receiver and you measure velocities. The way people measure anisotropy with velocity is that, I'll go through that later on in the class, but you basically measure along different directions. So you measure different components of velocity and then you get also the anisotropic properties. It's possible. But he makes some arguments why ROS is much better. What are these arguments?
Coupling is strong.
Actually, the coupling, you try to make it almost none. So in the way we do it, at least, you try just to place it loosely over very tiny point-like support points. So, Chaz, did you see the ROS setup at Los Alamos when you were there? You typically place the sample such that it's just standing almost, it's just stable. You try to minimize the amount of support or any kind of coupling, and you use this really tiny transducers to receive and to vibrate the sample. Excellent. So one thing that he says that there is no need to be worried about coupling. So he says ROS is better than ultrasound, like ultrasonic testing for this application. What else does he say? Which is related to what I just described. Transducer doesn't play any role. Whatever you are measuring, it comes from the material. So the effect of the transducer is minimized. So that's he also says something that may not mean much to you right now. He's saying that you use continuous wave excitation, and that is easier to analyze when you have low signal to noise ratio, meaning that your data is very noisy. This may not mean so much to you, but if you have very low signal to noise ratios, it's hard to see the arrival of waves when you measure velocity. But when you have a continuous wave, it's easier to just compare and look at the phase information to get the velocity or any changes from the phase of the continuous wave, because you can very easily reconstruct it. You know what frequency it is. So that's the kind of a subtle things. And then he talks about the application, but probably those applications are not very interesting for most of you, the ones he's mentioning. But something that you need to know is that this gives elastic constants. And there are, I'll show you in a second that there are much simpler versions of this kind of test, which can give you elastic information about elastic constants. And that's why resonance matters. And that's why we start talking about resonance as the first thing. It's easy. Any questions you had when you read the paper now? It is up to you. So when we go to the lab, I'll show you. You can, that depends on what range you choose. So you can get as many modes as you want, as long as they are above noise level. So you have to have the right amplitude and you can have it. Now, your question is very valid because even if when you have a linear elastic material, you approximately, my experience, you need to look for at least 10 modes to get good results, to get very good, because the inverse problem is not That's what Jay is not mentioning in his paper, is that solving this inverse problem is not very easy, especially if the material is very attenuated. It becomes a really hard thing to do. So the person that he mentions at Los Alamos, Migliori, was his grandson still at Los Alamos when you were there? Migliori? Yeah, so he was studying there. He has written a book. You can, I think it's even online for free, just on Ross and how you actually get elastic constants from those measurements. So it's pretty complicated. Right now it's easy. You just use MATLAB. You just use nonlinear optimization. It's easier, but it's an ill-posed problem. So it's very hard to. You have to have 10 if your material is linear elastic. So you are only looking for 2 constants. Right. Yeah, you need to look for. And the way we do it, you try not to just look at one position. You change the position of the sample a little bit, slightly, so you still have free boundary conditions. But you change things a little bit so you get a few different data sets and then you analyze the whole thing to get good results. There is a lot of art involved in measurement. Yeah, he doesn't mention that, but of course he's very careful. I've taken some measurements with him here. It was really a pleasure to work with him. So now, any other questions about this paper before we move? Oh, the number of constants. This was Tim's question. So he asked me that on Tuesday. So I'm very prepared to answer this question. It's clear what 81 where it is coming from. It's because of the symmetry. So from 81. Let's say if we write it in the Einstein notation, so it's easy to go to 36, I think. Because let's say in engineering terms, sigma 1, 2 and 2, 1 are the same. 1, 1 and 1, 1 is the same. So there are certain symmetries that we have. Then you go to 36, and then you have the ones. Basically, let me show you. You have the ones on the diagonal, and if your material is completely anisotropic, then half of the tensor. So if you consider a 6 by 6, if you count the number of elements here, that's 21. But we have normally much less than that. But this is when it is very anisotropic. Is this clear now, Tim, also for you?
Because everything's mirrored on the
right.
asymmetry on the other side.
Exactly. Because the stiffness matrix is symmetric. So should we count those to make sure it's so it is 36. Oh, because of these symmetries. Because I don't know, in engineering terms, all you are left with are these ones, like sigma. Let's say sigma 1, 1, sigma. Let's write it nicely. Sigma 2, 2, sigma 3, 3, and then sigma 1, 2, sigma 1, 3, sigma 2, 3. All the other ones are symmetric. So when you have 81, that means that that's all of them. 1, 1, 1, 2, 1, 3, then again 2, 1, 2, 2, 2, 3. So it would be 3 times 3, which is 9. 9 times 9 is 81. So that when there is no symmetry, no nothing. But we know that this is not the case. Exactly. So what we have are typically only these. These are the ones which are independent from each other. And then these are only 6. So your matrix is like 6 by 6, but then it is symmetric. So you have the 6 on the diagonal, and then you have half of the elements. So it's 15 plus 6, which is 21. Is this clear to everyone else? Yeah. Don't worry about it. This is not essential in understanding this paper. But yeah. Any other questions, concerns about this? Okay, so now I like to kind of maybe, instead of just jumping to the equations, to tell you a little bit more now, other than the paper that you read, why resonance matters. And then we start developing the equations from a basic system, and then we go to the systems that are important in our applications. So, since we have a mix of students in the class from different backgrounds, I thought it's important to show you different applications of resonance. So, Jay also mentions this in his paper, that they even use something like ROS for a bridge. So in a structural health monitoring, which is important to some of you, at least Mervin, probably that's something you are interested in, and Anurup, that's something you have heard about, and Ryan. So you see that you have a bridge, and the purpose of a structural health monitoring is to monitor something about the bridge and to find out, for example, where in the bridge something is going wrong, so that you are prepared to take actions. So the most prominent way that people do it is actually using resonance. And the way they do it is very similar to the diagram I just showed you for ROS. It's just extremely similar. So the way it's being done is that you take the bridge, the whole bridge, you simulate it in finite elements. So you see here, this is not a real bridge, that's the simulation. You put all the elements which matter and all the cables, etc. in your huge finite element simulation, and then you look for natural frequencies. That's what you do. So this is very similar to that forward model that I told you. It's just at a different scale. It could be the moon, it could be the earth, now it's the bridge. Can be any of that. So let's look at these mode shapes a little bit, especially if you never saw one. You remember I gave you one quiz with a mode shape in it? So these are kind of different mode shapes. You see something here written like bending modes or torsional modes. That relates to the way of, you see that how the elements are forming. For example, the bending modes, look at the elements, how they are forming. One thing that you can see is that one thing that I want you to think about mode shapes, think about them as some sort of waves with wavelengths very close to the length scale of the object, in this case the bridge. Again, it's very important that you start looking at the mode shapes as waves with wavelengths of the length scale very close to the object that they are propagating into. they are not really propagating. You will see that soon. They are like a standing waves, but it's very useful to think about them that way. And that's why resonance and wave propagation are sisters. They are very close in terms of concepts and what's going on. And what you see is that now how this is being used in a structural health monitoring. If you, for example, if you look at the center of this bridge, you see that in some of the modes, that center is completely still. It doesn't move. But in some other modes, it's actually moving the maximum. So what does that tell you? It tells you that if you are looking at a mode where that particular point has a very high displacement, whatever that is related to that mode is related to the material properties around that location. I'm not sure I said what I wanted to say, but different modes have different displacement distribution throughout the structure. So let's say, for example, if you look at the first bending mode of this bridge, you see that the center of the bridge is moving a lot. So now, if you compare your measured first mode to the simulated first mode, and you see a lot of difference between them, that would mean that the material properties in the middle of the bridge may be very different from what you would think they are. That could mean that they may be deteriorated. Maybe the bridge at that location has some big problem. The concept is clear? Anurup? Yeah. So that's how people, I jumped one too much. That's how people look at, this is what you see here is a difference between, just to show you the concept, that's the difference between a measured and a simulated mode shape, stacked. And yes, you need to do optimization to look at these differences. So you simulate the bridge just like J is simulating for resonances of his tiny crystals. You simulate it, you get the mode shapes, you measure the mode shapes. That's hard. And then you look at the difference. And from that, you get to see which element. You see, there are elements where you see that the elements throughout the bridge where the differences are more. And then you conclude that maybe something is wrong there. This is what people use in a structural health monitoring. The last part is element number and uses, yes, for that particular element, if you change the material properties, what would be the change between the simulated versus the measured? That's how you kind of localize it. It's not very easy to do. And not, yes, please. Well, for each mode you do that, and that kind of tells you where the problems are. So, for example, if you see that the example I made was if you see that the maximum difference is in the first bending mode, that could tell you that the problems are in the middle of your bridge. Typically, in that case, people try to go a little bit closer. Then you divide it into a number of elements, and then you go element by element, change things, and do this until you localize it.
You can also compare the frequency, where actually it is resonating and where you are getting simulation results.
But that's what you do. The resonance frequency, then you cannot localize it. Yeah, you do that too, but you cannot localize it. So that's kind of, this is one step further. Definitely, that's the first thing you do. This is being done also in buildings. It's very easy to measure this kind of resonance. What is in buildings, typically you just model it as one fixed free element, and then you place this triaxial accelerometer on the roof, and then you get the whole resonance of the building. So on a roof, for example, for buildings, that's typically people just look at the resonance. They don't try to locate, because you want to see if the whole thing has changed. You can place one accelerometer on the top and one at the base to decouple the structure and soil interaction from the whole thing. But you look at that. This is another study where you see that for a building, that's where you can actually see the experimental versus numerical modeling. So the mismatch kind of gives you where things can go wrong. It's useful for monitoring. Once you have validated your model, then you look to see what's going on. Something that is very interesting to me, and maybe to the geophysicists in the class or people who work, is this nonlinearity effect. So just like what some of you know happens in the Earth, there are observations of nonlinearity of resonance frequency also for buildings. This is fascinating. I have to say that the person who has made this measurement is a geophysicist, Philip. And what are we looking at? Here, you have a building. You are continuously monitoring this natural frequency of the building, and then an earthquake happens. This is what I taught you last time, something similar to that you are actually looking at the change in resonance with time. So it's like a time frequency kind of picture. It's not exactly a spectrogram, but it's something similar to that. So look here, you see a drop of the resonance frequency, and then you see an oscillations when the earthquake, during the time that the earthquake was received, and then you see that the building recovers. So this, in the lab, we have seen that the slope of this recovery tells a lot about the level of damage inside the material. So whether it's building or the earth or a piece of concrete that we tested in the lab, if you heat it and you look at this drop and recovery, if your material is damaged, the drop and the rate of recovery would be different from when it is intact. But this is another way of monitoring what's going on with the building. For example, you see that the resonance drops, so the material becomes softer, but then you also see that it kind of goes back to where it was before. So that's kind of an assurance that the building is not totally damaged in a way. So resonance is very useful in a way here. And if you are familiar with some standard experimental setups, you may have seen that. Does anyone know this kind of testing? I don't know if you learned this in rock testing, rock physics. I don't know that. Do you do any kind of resonance testing to test the rock? So I actually saw at AGU that people had used ROS for measuring the properties of an ice cube. And they were very excited, and everyone was very excited. I mean, I think for the community, maybe it's not as obvious that it was when I saw it, I was like, "Ah, cool!" But it's something that people have used for many years. No. So you may know that there are some standard testing methods that work on resonance. Just you use a tap, you pick up the acceleration, and from the resonance, you magically you come to the elastic constants here. So the idea is where this is coming from. And this one we talked about, Ross. There is another paper, which is probably easier to read, about with more details on how to go from the spectra to the elastic constants, if anyone is interested in that. So you can see that how the different modes of vibration look like, and how, let's say, typical resonance curves look like. Now, this is just basically motivation to tell you why we are learning about vibration. And what I hope to teach you about vibration under this elementary system is very quickly to go over the dynamics of single degree of freedom systems. That's something probably you are familiar with, but it would be a good reminder. And then we discuss resonance and damping ratio. And then we go to forced vibrations. That's very interesting also. And we talk about damping ratio and Q factor. And at the end, I want, as an application, then I want to show you how an accelerometer works. If you do any kind of testing which relates to vibrational measurements or relates to sometimes even acoustic measurement, you would need to use an accelerometer. So as an application of what you have learned, then we look at accelerometer. Okay, any question about what I showed you, the introductory material? Now, I haven't posted the notes so far because I feel like it's good to write things down, especially if you want to remember. So let's just start with a very simple case, and that is the undamped vibration of a discrete mass system. So I call this a discrete mass system because in the next module we look at the continuous mass. So you have a mass, you have a linear spring. Let's mark the equilibrium. That's where everything is in equilibrium. And I don't know why, but I chose the Z for the movement of mass from equilibrium position. So how do we get the equation of motion for this? Try to see if you can draw the free body diagram for that. Is this terminology free body diagram? This is the same all over the different disciplines you are coming from? Great. So yeah, try to write the equations. It's very, very simple, but it's a nice warm-up. So the forces which act is very simple. If we move this a little bit down, the spring wants to bring it up back again. And then you have the inertia force. It's not a real force, so I put it like this. And then you can write the dynamic equilibrium. So question? Z double dot is the acceleration. So it's inertia. Yeah, that's a very good question. It's vertical, doesn't matter. Why there is no gravity? No, let's say this is hanging here.
But it's already, these already, and
Yes. That's why I said this is equilibrium. That's a good point. So if I add the equilibrium, then I would have another term in Z, then they would cancel out. Because imagine you have a mass, you hang it from a spring, you let it settle. When it's not moving anymore, then you just very slightly you pull it and then you let it vibrate. So you start from where it already the spring force is already in equilibrium with the weight. Z is the displacement, exactly. But you have seen this before somewhere? No? It's fine. It's a long time ago, don't worry. That's why I'm writing it. After giving you that quiz, I decided where to start, so don't worry about it. So now, how do we solve this? If you know this, it's kind of easy. If you have never seen it before, it's not hard. You just divide both sides by m, and then we call this omega squared. This is a kind of a famous equation. It's second order because we have z double dot. And it's a linear equation because we don't have any terms which are like multiplication. So we have z and z double dot. So the solution to that is something like that. Where what are A and B? For that we have to look at what is called initial conditions. And we need to talk about omega just a little bit because this turns out to be a very important thing. And we can gain some intuition even in this very, very, very simple system. Omega squared is k over m. So omega is square root of k over m. So k is stiffness, and m here is the lumped mass. Here we just have a discrete mass. So it's, this omega, what does this tell us? The response is A cosine omega t plus B sine omega t. What did we call this kind of time signal? Exactly 2 weeks ago, 3 classes before. It's a periodic response. What is omega to that periodic response? What is it? Omega? It is the angular frequency. This one is undamped right now. We are still looking at a simple case of undamped, but omega is the frequency, right? It's the frequency of. So what does that tell you? What is the meaning of that? before when you learned this, probably you just wrote it down and then you learned it. But now you have to kind of understand what's going on. What does it mean? It means that if you take a system, now this is a simple system. If you take a mass, connect it to a spring, just let it settle, slightly pull on it, and then let it vibrate, it's going to vibrate with a frequency equal to omega, angular frequency. So this is the concept of natural frequency. That means that there are no other things involved. The system is free. You just tap it, you just perturb it in a way, and you let it go. And when you let it go, it excites at this frequency. It's the natural frequency of this system. It's the angular frequency. You told me, Song, that you use a different term, intrinsic frequency, in your domain, you told me. You remember after the quiz? Something... No? When I asked you about resonance, I remember that. Maybe I don't remember this right, but some different people, depending on the domain, have different names for it. But natural frequency, whatever. Now, let's look at this a little bit more. It's very simple, but what do you see here? The natural frequency depends on the stiffness and mass density. Think about Jay's paper again. If you know the mass, and if you measure the frequency of the system, somehow magically you can get the elastic constant. It doesn't seem to be too magical, because you can even see in this small system the relationship between frequency and stiffness. So you see where this is going to go. Of course, this system has only one natural frequency. It's a very simple system. Okay, now, since we know now a lot about signals, etc., of course we have to think about this response a little bit more carefully. Sorry about this cut off. I decided to use my own handwriting as a picture because I cannot draw it here. Anyway, what I'm plotting here for you is basically this response. The blue curve is the response. So the response, we saw that it is A cosine omega t plus B sine omega t. What I haven't told you so far is what A and B are. So to know A and B, typically in this kind of any kind of vibration case, you need to know the initial displacement and initial velocity. So initial displacement, let's call it z0. That means z at time equal to 0. And initial velocity, I use dot for derivative with respect to time. So it is z dot at time equal to 0. So if you take the derivatives, and this is easy, z equal to 0 becomes a. So immediately a becomes z0. And then the derivative of the second one is b omega at t equal to 0. So b also becomes clear. So this response becomes initial displacement times cosine omega t. That's very interesting. Plus the initial velocity over the natural angular frequency of the system times sine omega t. So basically, if you know how much you are pulling on your system, and if you know how fast in the beginning, you know everything about this. And the blue curve that you see here, the blue, is this response. What is the amplitude of this response? Yes, I heard a square, that's good enough. A square root of, exactly. Just to check. Now the red is the sinusoidal part, and the black curve is the cosine term. And so omega, so what you see here is that this is periodic. So if there is no friction in the system, it's just going to go forever. It's periodic. The relationship between the period of vibrations and omega, it's also given here. It's useful to write this in a few other ways for later on. If you want to go to seminar, it seems that it's the time. Okay. Me too. So it's we are in. It is fun. Yeah, so great. I'm afraid of Chris to say, oh no, I'm just joking. But next week I will go to seminar too, so we'll finish all of us, because I want to see Chaz's presentation. So this response, you can see that both sides are both components. The frequency is omega, and then this can be written as just a sine or a cosine. This is kind of what I was teaching you in the beginning. So you can see that the sine one, you can see the blue curve. You can look at it as a sinusoidal if you take into account this phase. So it would be sine omega t plus alpha, right? Or you can write it as cosine. It's a good practice just to see that, and this would be the phase. And you can see what this alpha and beta are. I mean, you can get this yourself. Now, I give this to you. So, for alpha, you just have the initial displacement over initial velocity over omega, and for beta, it's kind of the opposite. Now, the reason I'm showing you this is something more important. A lot of times, it's very useful to express things in exponential or in complex form. So this is very easy to see that z can be written as the real part of ci omega t minus beta. So the real part of this exponential. Because you can see that the real part of that is a cosine. Why we like exponentials? Because it's very easy to calculate derivatives with exponentials. They're great. So it's very useful that you kind of get used to seeing exponentials instead of sine and cosine. And let me see. It's maybe in parentheses or somewhere if you maybe forgot about this, which is completely fine. That there is a relationship, like a exponential, a complex exponential is like the real part is a cosine term and the imaginary part is a sine term. This is very useful in everything we do from now on. So I kind of started with real, but kind of most of the other stuff. Another thing that I find useful is that that you think about sometimes. Look at this sine and cosine terms here that you see. You see the red and the black curve. It's sometimes useful to think that the sine is think about them as vectors. That the sine lags behind by pi over 2 from cosine. If you just look at it, this becomes clear. Why? Right? You have the red, and you see that the cosine is pi over 2 ahead because the peak comes first, and then for cosine it takes pi over 2 to get to the peak. For that reason. So, yeah. I wrote down again the kind of the solution in complex form, but this may not be too necessary. I don't know. We could write it if you like. So if we have this kind of equation, you can start by this. Instead of saying sine and cosine, you can just start with a solution like that. And if you do the derivatives, this is kind of useful. You see that the derivative is just I omega times displacement, and in physical terms the derivative is velocity, and this is displacement. So and you see that if you multiply the displacement by I omega, you get the velocity. Now again, if you think about vectors, it means that the velocity and displacement are pi over 2 out of phase. Yes? Does it? That's very useful to have kind of as a concept. How about the acceleration? Well, you take another derivative, try to see if you can still calculate derivatives. It's sometimes we forget, and you see that the acceleration is actually, so if you can think about it in a vector way, it is as if acceleration and displacement are kind of on the same axis, but acceleration is always negative of displacement. Because you have omega squared, which is positive, so that's always negative to the other side. This is kind of useful in everything we do to just know. And of course, you can see that this satisfies this equation. And if you do the boundary conditions, you can get C I've kind of done this, so let me do this nicely. If you do the boundary conditions saying that, okay, we have initial displacement and velocity, then it's easy to show that C, of course, as you would expect, you get the same thing. As you had before, and you get phi it looks just like beta. So we move from here by adding more complexity to this system. Let's say looking if we have viscous damping, what happens? So here you have a dashpot. So I leave this for Tuesday, I guess.